stochastic process. This is a Module 5 Lecture 4 MM1 queuing model. In this talk I am going to discuss the queuing models. So, for that I am going to give the introduction to the queuing models, then I am going to discuss the Kendall notation, then followed by that the simplest queuing model MM1 queue will be discussed. And this is going to be the applications of a continuous time Markov chain in queuing models. So, in this lecture I am going to discuss only the simplest queuing model MM1 queues. So, how one can define the queuing system? You can see many examples in which whenever you go to the supermarket to get some items, or you see the railway station counters, or you can see the computer service center, many PCs are there and printers and so on. So, how the queuing system is created, and also you can see the examples in the calls allocation in telecommunication systems. In all those examples you can see something is getting served and leave the system. We can give the queuing system, we can represent the queuing system in a pictorial form. Some customers are coming into the system and waiting for their service. Once the service is over, then they departure from the system. So, this is the way one can visualize the queuing system in a pictorial form. This is a diagrammatic representation, and the x axis is the time and y axis is the number of customers in the system. Suppose at time A1 the first customer enter into the system, then the number of customers in the system is incremented by 1. The customer who entered the system is getting the service. During his service time, the next customer enters the system, that with the time point A2. Therefore, now the number of customers in the system is 2 going on. At this time point, the first customer service is over. So, he departure from the system, that is D1, the time point in which the first customer service is over. Now, the number of customers in the system is 1. The time point T suffix 2, the second customer service also gets over. Now, the number of customers in the system is 0. The third customer entered at the time point A3. So, during this interval the system was empty. So, like that the system is keep increasing whenever one customer enter into the system, and decreasing by 1 whenever the service is completed. So, this is the diagrammatic representation of any queuing system. Here I made the assumption it is a very simplest one, only one customer entering into the system and only one customer is getting served and leave the system and so on. So, this is the simple way of simple diagrammatic representation of the queuing system. So, to define the queuing system you need a few important characteristics. Using that one can easily frame the queuing system. So, for that you need the first information, that is arrival pattern of customers. How the customers are entering into the system, how frequently, whether the customers are coming in a very constant interval of time or in a random fashion. If it is constant, then we say the inter-arrival time is deterministic. If the customers are entering into the system with the inter-arrival time, that is some random variable, then we should know what is the distribution of inter-arrival time. So, this information is needed to define the queuing system, the arrival pattern, that includes whether it is a deterministic or probabilistic If it is a deterministic, then what is the inter-arrival time, that constant time. If it is a probabilistic, then what is the distribution, and so on. Similarly, after the customer is entering into the system, you should know how the service takes place, whether the service time for each customer who enter into the system, is it a constant or random. If it is a constant amount of service for each customer, then what is the time, how much time it takes for each service. If it is a probabilistic, then what is the distribution of service time. Then the third important information or the characteristic is a number of servers in the system. How many service channels are available to do the service, whether you have only one server in the system or more than one or countably infinite numbers. So according to that, the queuing system may vary. So the third information is number of servers in the system. The fourth information, that is a system capacity, whether the capacity is a finite one or infinite capacity. Accordingly, the number of customers in the system may go maximum the finite capacity, or it may infinite number of customers can wait in the system to get the service. Therefore, the system capacity is also important characteristic. The fourth one, queuing discipline. When the customers enter into the system, whether they are getting served or whether they are placed in a first come first order or first come last service or random fashion or priority based and so on. So the queuing discipline also important to know how the queuing system is at any time, to know the dynamics of number of customers in the system, and you should know how the queuing discipline is taken care. Similarly, the service discipline also, how the services also takes place during the picking the customers for the service. So these are all the minimum important information is to characterize the queuing system. One is the arrival pattern, second is the service pattern, and the third is the number of servers. The fourth is the capacity of the system, and the service discipline or queuing discipline. So based on that, the Kendall made a notation, and that notation is called the Kendall notation. The Kendall notation consists of capital A, that letter A, slash capital B, slash capital X, slash capital Y, and capital Z. So the possible values we are going to assign for A, B, X, Y, Z, accordingly one can define the queuing system. And each letter is corresponding to some important characteristic of the queuing system. A denotes the arrival pattern information. Here the A denotes the distribution of inter-arrival time, the letter corresponding to the capital A. The second one, capital B, whatever the letters you are going to assign for the second one, that denotes the distribution of the service time. The way I have said the characteristic, the first one is arrival pattern, second one is service pattern, and so on. The same way we have given the Kendall notation. So the capital A is for the letter, whatever the letter you are going to assign for capital A, that is for the distribution of inter-arrival time, and B is for the service time distribution. The third one, X, whatever the number you are going to write, that is the number of servers in the system. The fourth one, what is the capacity of the system. The fifth one, what is the queuing discipline, whether it is a first come first served, last come first served, priority, random, and so on. Now I am going to give what are all the different possible values for these letters. The first two, A is for the distribution of inter-arrival time, B is for the distribution of service time, the both can be chosen from these letters. If you write m in the first place, that means the inter-arrival time is exponentially distributed. Even though it is exponentially distributed, we use the letter m because of exponential distribution satisfies the memoryless property or Markovian property. So, to denote that, we use the letter m. So, whenever you write m in the place of a or the second place b, then that means the inter-arrival time is exponentially distributed or service time is exponentially distributed respectively. Suppose you write the letter d in the place of a or b, that means that distribution is deterministic. That means it is going to take, it is not a probabilistic, it takes a constant amount of time whether you placed it in the first or second accordingly. So, it is going to be a constant amount of time going to take for the inter-arrival time or service time whenever you place it in A or B respectively. Similarly, if you use the letter E suffix k, that means it is a Erlang distribution of type k, or we can say Erlang distribution of a stage k, that can be 1, 2 and so on. That means the inter-arrival time is Erlang distributed with the stage k if you place it in the first letter. Similarly, h suffix k means a hyper exponential distribution of a type k. Whenever you have a inter-arrival time is other than exponential, deterministic and so on. So, usually other than exponential you can use the letter g. G means a general distribution. General distribution is also, it's a known distribution, the only thing is it is other than exponential distribution. So, either you can use the letter m, d, e, k, h, k or g. So, g can be other than m itself in the usual or in general form. It is a known distribution that other than exponential we use the letter called g for general distribution. So, these are all the possible values for the A and B, whereas the third one is the number of servers in the system, and the fourth one is the capacity of the system, and the fifth one is the queuing discipline. The default discipline is first come first served, therefore, no need to write the fifth information. And the sixth information is also there, what is the population of the customers who are entering into the system. The default population is infinite. That means from an infinite source the customers are entering into the system, that is the sixth information. As long as we won't write, as long as the system in which the population is infinite as well as the queuing discipline is first come first served, then we won't write. So, we write only the first four information, that is inter-arrival time distribution, second one is service time distribution, the third one is number of servers, and the fourth information is capacity of the system. So, in these examples the inter-arrival time and service time both are exponentially distributed, by default they are independent also, and the third letter denotes number of servers in the system. So, here only one server in the system. Here C means it can be greater than or equal to 1, that is multi-server system, and fourth letter K means the capacity of the system. Suppose we did not write the fourth information here, that means it is a infinite capacity system, and this is also infinite capacity system. And since the inter-arrival time and the service time are exponentially distributed, this model is called the Markovian queues because it satisfies the Markov property. Whereas non-Markovian queues, either service time or the inter-arrival time can be a non-exponential distribution, or non-exponential distribution. In default you can use the letter general distribution. So, whenever G comes in the first place or the second place, then we use then we say it is a non-Markovian queues, and if the fourth letter is missing, that means it is a infinite capacity system. There are many applications of queuing system. We are going to discuss the abstract queuing system in the further lecture. The easiest or the simplest queuing model, that is a Markovian queuing model, that is MM1 queuing model. Later we are going to relate with the birth-death process also. In the MM1 queuing model, the inter-arrival time is exponentially distributed. As I discussed the Poisson process in the previous lecture, whenever you have a arrival follows a Poisson process, then the inter-arrival time follows a exponential distribution and are independent also. So, here the first information is a arrival process follows a Poisson process with the intensity or rate lambda. That means the inter-arrival times are independent and each one is exponentially distributed with the parameter lambda. The second information, that is service time. Service times are exponentially distributed with the parameter mu, and the service times are independent for each customers, and that is also independent with the arrival process. That means there is no dependency over the arrival pattern with the service pattern. Service times and the inter-arrival times are independent. Then the third information, only one server in the system. That is a queuing system in which only one server, and the fourth information is missing. That means it is a default, it is a infinite capacity model. Infinite capacity model. Now our interest is to find out the behavior of a queuing system or the behavior of number of customers in the system at any time t. Therefore, you can define a random variable n of t, that is nothing but the number of customers in the system at time t. Therefore, this is going to form a stochastic process over the t. Since the inter-arrival time is exponentially distributed and the service times are exponentially distributed, the memoryless property is going to be satisfied throughout all the time. Therefore, this stochastic process, there is a discrete state continuous time stochastic process satisfying the Markov property. Therefore, this is a Markov process. Since inter-arrival time is exponentially distributed and the service time is exponentially distributed and both are independent and the service time is also independent for each customers. Therefore, this stochastic process satisfies the memoryless property at all time points. Therefore, this discrete state, because the possible values of n of t, since it is a number of customers, the possible values are 0, 1, 2 and so on, countably infinite. So, therefore, it is a discrete state and you are observing the system over the time, therefore, it is a continuous time. Therefore, this stochastic process is a discrete state continuous time stochastic process satisfying the Markov property based on these assumptions. Therefore, n of t is a Markov process. Since the state space is a discrete, therefore, this is a Markov chain. Therefore, this is a continuous time Markov chain. Therefore, n of t is a CTMC. So, one can write the state transition diagram for this CTMC. That means the possible states are 0, 1, 2 and so on. So, this will form a nodes and you try to find out what is the rate in which the system is moving from one state to other state. Since it is a MM1 queuing model, therefore, whenever the system is in the state 0, by the inter-arrival time which is exponentially distributed, the number of customers in the system will be incremented by 1. Therefore, that rate will be lambda, or the system moving from the state 0 to 1, it spends exponentially distributed amount of time here before moving into the state 1. Once the system come to the state 1, either one more arrival is possible, or the customer who is under service, then service could have been finished. Therefore, the service time is exponentially distributed with the parameter mu. Therefore, the system goes from the state 1 to 0 with the parameter mu. Similarly, from 1 to 2, because of the inter-arrival time is exponentially distributed with the parameter lambda, therefore, this is lambda. Since the arrival follows a Poisson process, in a very small interval of time, only one customer is possible with the probability lambda times delta t and so on. Therefore, there is no way the system goes from one state to jump into more than one state. That is not possible forward. So, only one step forward is possible because of the arrival process follows a Poisson process, and since we have only one servers in the system also decremented by only one level below. Therefore, this is going to form a birth-death process. The reason for this CTMC going to be a birth-death process, because of the arrival process follows a Poisson process. So, whatever the assumptions we have it for the Poisson process, that is going to be satisfied. And since we have only one server in the system and he does the service for only one customer at a time, after finishing that server, after finishing the customer's service, then it move into the next service immediately and so on, if the customers are available in the queue. Therefore, the system goes to the one state below by only one move only. It won't move from 2 to 0 or 3 to 1 and so on. Therefore, this CTMC is a birth-death process. Therefore, I am connecting the CTMC with the MM queue, in particular the CTMC with the birth-death process. Because of the transitions due to arrival or departure of a customer, and only nearest neighbors transitions are allowed because of the assumptions which we have made. Therefore, this is going to be a continuous time Markov chain with the rate in which the system moves from the state I to I plus 1, that rate is lambda, and the system moves from the state I to I minus 1, that rate is mu, and all other rates are going to be 0 other than the diagonal element, and these rates also constant, not state dependent rates. Therefore, this is a birth-death process with the birth rates lambda and the death rates mu. So, this is a sample path. Suppose at time 0 one customer in the system, then service is over, then the second customer enter into the system. Now, the number of customers in the system is 1 and so on. So, that means that this duration is the service time for the first customer, and from this point to this point, that is the inter-arrival time of the second customer entering into the system, and from this time point to this time point, that is the service time for the second customer, which is independent of the service time for the first customer, and this is the time point second customer enter, and this is a time point in which the third customer enters. Therefore, the inter-arrival time is from this point to this point and so on. So, this is the dynamics of a number of customers in the system over the time. Therefore, this stochastic process is a discrete state continuous time stochastic process satisfying the Markov property. Therefore, this is a continuous time Markov chain. So, later I am going to simulate the MM1 queuing model using some simulation technique. So, the conclusion is the underlying stochastic process for the MM1 queuing model is a birth-death process. The N of t is a stochastic process. So, this stochastic process is a birth-death process. Therefore, now we are going to discuss the stationary distribution, time dependent probabilities and so on. So, how to find the stationary distribution? Solve pi q is equal to 0, pi is the vector, consists of pi i's, where pi i's are nothing but what is the probability that n customers in the system, what is the probability that I customers in the system in a long run. So, that long run is defined in this way. The n of t is a stochastic process. As t tends to infinity, the number of customers in the system in a long run, that is going to be the n, and pi a is nothing but a probability that n I customers in the system in a longer run. So, now we are going to solve pi q is equal to 0 with the normalized equation summation of pi a is equal to 1. So, once you frame the equation, you will get a pi 1 in terms of pi naught and the pi I minus 1 in terms of first pi I, then substitute recursively, you will get in terms of pi naught. So, since it is a homogeneous equation, you will get all pi i's in terms of pi naught. So, use the normalizing equation summation of pi a is equal to 1, you will get pi naught. So, the pi naught is equal to 1 minus rho, where rho is lambda by mu. And since I am relating this stochastic process with the birth death process with the infinite capacity, if you recall, the stationary distribution exists as long as the denominator of pi naught, that series converges. So, that will converge only if lambda by mu is less than 1. If lambda by mu is greater than or equal to 1, then that denominator diverges. Accordingly, you will not get the stationary distribution. So, to have a stationary distribution, you need rho has to be less than 1. That also you can intuitively say, whenever the system is stable, that is corresponding to rho is less than 1, in that you will have a stationary distribution. That means in a longer run, this is a proportion of the time the system will be empty. And the pi n is nothing but the n customers in the system in a longer run, that is 1 minus rho times rho power n, where rho is less than 1. This rho can be visualized as the offered load also, because the rho is nothing but the mean arrival rate and the mu is the mean service rate, and this ratio will give the offered load. And 1 minus pi naught, that is the probability that the system is non-empty, and that is nothing but the server utilization. Server utilization is nothing but what is the probability that the server is busy. The server will be busy as long as the system is non-empty. So, the rho is the server utilization that can be obtained in the from this formula, and in a longer run the server utilization is rho. Other than stationary distribution, one can find out the average measures also in the system. So, suppose you make a E of n, that is nothing but the average number of customers in the system in steady state. Since you know the probability distribution, substitute pi n's here, therefore, n times pi n summation over n, that is going to be the average number of customers in the system. If you do little simplification, you will get rho divided by 1 minus rho, where rho is less than 1. So, this is the average number of customers in the system, and also one can get a variance of the number of customers in the system also. For that you have to find out the E of n square, then using that formula you can get the variance of n also. So, here we are getting a mean and variance of number of customers in the system in steady state. Also one can find average number in the queue. So, the letter q is a random variable, and here we are finding the expectation of q, that is average number of customers in the queue. That means before getting the service, how many customers in the system? We have only one server in the system, and whenever the service is going on, and all other arriving customers will be queued. That means when n plus 1 customers in the system, n people are in the queue. Therefore, summation n times pi n plus 1. Do the simplification, you will get average number of customers in the queue also. You substitute the pi n plus 1 from the one I have discussed in the stationary distribution. Here I am going to relate the average measures using the Little's law. This is proven by John Little 1961. This is valid for any system in which arrival comes into the pattern with the arrival rate lambda, and R is the time spent in the system and leave the system after the service or whatever the things are over. Then in a longer run one can say the arrival rate multiplied by the average time spent in the system, that is same as average number in the system. So, this relation is valid for whatever be the underlying distribution, whatever be the underlying distribution of the service, underlying distribution of the arrival. What it says, if you have a system in which the arrival rate is a mean arrival rate is lambda and the mean time spent in the system is expectation of R, then that product will give average number in the system. So, indirectly it says whenever the system has a long run in a stable system, the expectation of a average number of customers during the interval 0 to t as a t tends to infinity, that is going to be have a limit expectation of n, and the arrival rate lambda of t, that also has the mean arrival rate as a t tends to infinity, that is also going to be a sum having a limit constant lambda. And similarly the average spent by the customers in the system at any time t, and if you make a t tends to infinity, that expectation quantity also has a limit. Therefore, you will have a lambda times expectation of R is same as expectation of n. Now, using this Little's law, I am going to find out the measures for the MM1Q model. So, suppose R denotes the time spent in the system by the customer and W denotes the waiting time by any customer in the system. Then I can use the Little's formula, the Little's law in the previous one. So, if I know the mean arrival rate and if I know mean number of customers in the system in a longer run, using these I can find out the average time spent in the system. If I know to use using Little's law, if I know the average number of customers in the system longer run and if I know the arrival rate, then I can find out the average time spent in the system in a longer run. Similarly, I can, once I know the average time spent in the system, if I subtract the average time of my own service, then that is going to be the average time waiting in the queue. So, this is average time waiting in the queue, that is same as the average time spent in the system minus my own average service time. In the MM1Q model, the service time is exponentially distributed with the parameter mu, therefore, the average is 1 by mu. So, the difference will give the average time waiting in the queue by any customer. Not only the average measures for the MM1Q, one can find out the actual distribution for R as well as W also, because this is a very simplest Markovian queuing model, whereas for all other models it is little complicated, but still one can get it. So, this is the easy model in which one can find out the distribution of the time spent in the system as well as the time or as well as the waiting time by a customer in the queue. First, let us go for finding out the distribution of waiting time. Waiting time means if no one in the system when you arrive, then your waiting time is 0, you are immediately going to get the service. So, the service time is your time spent in the system. Usually the time spent in the system is the time of your service plus the time of the waiting time. So, here I am finding the only the distribution of waiting time first. So, whenever the system is 0, your waiting time is 0. Whenever no customer in the system, the waiting time is 0. Whenever more than or equal to one customer in the system, then the waiting time is same as the remaining service time for the customer who is under service plus the customers in the queue before you join in the queue. So, those people service time addition plus the residual or the remaining service time of the customer who the first customer who is under service. So, this total time is the waiting time whenever the system is non-empty. Whenever the system is empty, then the waiting time is 0. Therefore, the W is a random variable, either it takes a value 0 or it takes a value greater than 0 based on the time of service of previous n people in the ahead of you. Therefore, W is a mixed random variable which has the probability mass function at 0 as well as a density function between the interval 0 to infinity. So, let me try for finding out the CDF of this random variable. So, the CDF is going to be 0 till 0. At 0 it has the CDF 1 minus rho, because when the waiting time is 0, that is equivalent of no one in the system. So, in the long run no one in the system, that is a pi naught, and the pi naught probability is 1 minus rho. The system is empty in a longer run, that is 1 minus rho. Therefore, the CDF at 0, that is same as 1 minus rho of, that is pi naught. Between the interval 0 to infinity, one we have to find out the distribution of W. Whenever n customers before you join in the system, that conditional distribution, the distribution of a W given the number of customers in the system is n, that distribution is nothing but the service time of the n customers, the first customer's remaining service time. The service time of the first customer is exponential distribution. The residual or remaining service time of the first customer, that is also exponential distribution because of memoryless property. So, this is exponential distribution. This is second customer service times, that is exponential distribution, and similarly for the nth customer also the service time is exponential distributed, and the way we made the assumption, all the service times are independent and each one is exponentially distributed with the parameter mu. Therefore, this is a sum of n independent exponentially distributed random variables. Therefore, the sum of n exponentials, that is going to be a gamma distribution with the parameters n and mu. There are many ways of finding out the distribution, but here I am just explaining through the distribution concept. This is sum of n independent exponential distribution. Therefore, you can conclude it is gamma distribution with the parameters n and mu. Once you know the conditional distribution, our interest is to find out the unconditional one. That means for t is greater than 0 and CDF at the point t, that is nothing but what is the conditional density, probability density, and what is the probability of n customers in the system. That multiplication with the possible n will give the CDF between the interval 0 to t. So, I have a density function of a gamma distribution, probability density function with the parameters n and mu, and this is a probability density function, multiply and integration between 0 to t, that will give the CDF, and the unconditional multiplied by probability of n customers in the system, that with the summation, that will give the unconditional. Therefore, the CDF is going to be summation n is equal to 1 to infinity integration 0 to t of the probability density function of a gamma distribution multiplied by n customer in the system. If you do the simplification, you will get 1 minus e power minus mu times 1 minus rho times t. Therefore, you can substitute here. Oh, here I made a mistake. So, here it is multiplied by rho. So, 1 minus rho times 1 minus rho times So, 1 minus rho times e power minus rho e power minus mu times 1 minus rho, that is going to be the So, once you are getting the CDF, you can conclude this is a mixed random variable with the probability mass at 0 is 1 minus rho and the density function between the interval 0 to infinity, that is rho times mu minus lambda times e power minus mu minus lambda times t, that is the probability density function for a distribution of waiting time. Similarly, one can get the distribution of a response time also, or the total time spent in the system. The total time spent in the system, that is nothing but that is a random variable, and the residual service time of the first customer who is in the system plus all the remaining n customers in the system in the queue plus your own service time. Therefore, here this is not a mixed random variable, this is a continuous random variable, because your service time is a continuous random variable which is exponentially distributed. Therefore, the R is going to be sum of your own service plus the remaining service of the first person in the system, if and so on till the nth customer who is in the queue. Therefore, this is the CDF of the random variable R. Here also one can argue, when n customer in the system before him who enter into the system, that is a sum of a exponential independent random variable and so on. Therefore, this is going to be a gamma distribution with the parameters n plus 1 mu. And for t greater than 0, find out the CDF using the first conditional, then unconditional multiplied by 1 minus rho times rho power n, summation over n is equal to 0 to infinity, because there is a possibility no one in the system or one customer, two customer and so on. Therefore, the running index is 0 to infinity. Do the simplification, you will get 1 minus e power minus rho times this. Therefore, you can substitute here, and if you see, the CDF is the same as the CDF of exponential distribution with a parameter that is mu times 1 minus rho. Therefore, you can conclude the total time spent in the system is exponentially distributed with the parameters mu times 1 minus rho. If you find out the average time, that is going to be 1 divided by the parameter, that is this. The same thing you got it in the average response time from the Little's formula, using once you know the value of lambda and expected number in the system, using Little's law you got expectation of time spent in the system, that is same result. So, here we are getting first finding the distribution of time spent in the system or response time, then we are finding the average time. Here I am giving the concept of output process. The arrival follows a Poisson process for the MM1 queue, and the service is exponentially distributed, which is independent of the arrival process, and the customers leave the system. Now, the question is, what is the distribution of the departure process? That means what is the inter departure time after first customer leaves, how much time it takes for the second customer leave the system, then the third customer how much time it takes for the inter departure time, and therefore, what is the distribution of the departure process? That is given by the Burke's theorem. The output of a Poisson input Q with a single channel having exponential service time and in steady state must be a Poisson with the same rate as the input. So, whenever you have a system in which the arrival follows a Poisson, and whenever the system has a single channel and the service time is exponentially distributed, in a longer run the departure process is also going to be a Poisson process, and the rate will be the same rate as the arrival process. So, this can be proved, but here I am giving the interpretation using the time reverse process, because in a steady state this model is going to satisfy the time reverse model. Therefore, the stationary distribution exists, and if you make this MM1 queuing model, the underlying birth death process satisfies a time reversibility equation. Therefore, using the time reverse you can conclude the departure process, you can reverse it, and that is going to be independent of the arrival process, and this is also going to be again Poisson process. So, using the time reverse concept, one can prove the departure process is independent of the arrival process, and departure process is also Poisson process with the same rate as the arrival rate. And even though I said it is a single channel having exponential service time, and this is valid for MM1 queue, the multi-server Markovian queue, as well as infinite server Markovian queue also. So, all those models can be combined with the single channel having exponential service time. Whether it is a single server or multi-server or infinite server, this result holds good. And the next result is the number of customers in the queue is independent of the departure process prior to it. That also satisfies. Now, we are giving the time dependent solution of a MM1 queue. There are many more methods to find out the time dependent solution for a MM1 queue. It started with the spectral method and the combinatorial method, and also the difference equation method. Like that, there are many more methods in the literature to find out the time dependent solution, and here I am presenting the time dependent solution by P.R. Parthasarathy, and this work is appeared in the Advanced Applied Probability volume number 19, 1987. So, in this paper he has considered the system of differential equation, that is nothing but the forward Kolmogorov equation, and making a simple function Qn of t, that is a difference of pi n's with the multiplication e power lambda plus mu of t. So, once you use this definition, once you convert this system of difference equation with the Qn of t by making a proper generating function, that is of the form n is equal to minus infinity to infinity Qn of t times s power n. Therefore, this is sort of a generating function in terms of Qn of t, where Qn of t is for n is equal to 1 to infinity, this is of difference of mu times pi n minus lambda times pi n minus 1 multiplication e power this function, and for n is equal to 0, minus 1, 2 and so on 0. Therefore, you have a generating function. So, you can convert the whole differential equation in terms of pi n into the one partial differential equation, with the initial condition also changes, because if you assume that I customers in the system at time 0, and this is going to be initial condition for function h of s comma t at t equal to 0. So, now the question is, you have to solve this equation with this initial condition, this PDE using this initial condition. So, use the some identity of modified Bessel function one can get the solution pi n of t in terms of pi naught, where pi naught you can get it in terms of q1, where all the qn's satisfies this equation, that is in terms of the modified Bessel function. So, one can see the complete solution in this paper, but here I am giving the very simple approach of getting the time dependent solution for the MM1Q by changing this system of differential equation into one PDE with the initial condition and solve that PDE and obtaining the pi n's and pi naught in terms of a modified Bessel function. Before I go to the summary, let me give the simulation of a MM1Q. So, this is a queuing network modeling lab. So, from in this queuing network modeling lab, one can simulate the queuing network models. So, for in this I am going to explain how to simulate the MM1Q, and the first experiment that is nothing but live simulation of a MM1Q single server, as well as you can simulate a multi-server queue model, and you can go for the infinite server model also. So, here I am simulating the MM1 queuing model. So, to simulate the MM1 queuing model, you need the information about the inter-arrival time, that is exponential distribution. You need a parameter lambda, the value of lambda, as well as you need a value of mu. That mu is nothing but the service rate. So, suppose you supply the arrival rate, suppose the arrival rate is 2 and the departure rate is 5, and the number of servers is a MM1Q, therefore, it is already 1 is placed, it is the number of servers. So, you can start . So, this is the way the system increases. So, this is the actual simulation, goes with the this is a time x axis and y is the number of customers in the system, and here the information is how many customers entered till this time, that is 15 customers entered and nobody is blocked because it is a MM1 queuing system, therefore, all the customers who are entering, it will be queued, and how many customers are served during this time, and the number of customers in the orbit. This is nothing to do with the MM1 queue, this is for the retrial queues. And now, how many customers are in the system at this time, and here this table gives the performance measures. The one we have calculated the average number of customers in the system, E of R, and the average number of customers in the queue, E of this is mean number of customers in the system, that is E of n, the mean number of customers in the queue, E of q, mean waiting time in the queue, that is mean waiting time, that is EW, mean sojourn time in the system, sojourn time, spending time or response time, all are the same. The mean sojourn time in the system is nothing but E of R. So, this is nothing but the E of R, this is nothing but E of W, this is nothing but E of Q, and this is nothing but the E of N, and the utilization is nothing but what is the probability that the so, here I am giving the runtime, what is the average values till this time, and what is the result is going to be in a longer run, in a steady state. And the blocking probability is here 0, because the system is a infinite capacity model, therefore, there is no one blocked, therefore, the blocking probability is 0. So, this is the way we can reset, and you can give some other values, and you can start again and you get the another simulation also, and initially it gives the fixed steady state results in the steady state theoretical result, and the runtime is nothing but what is the result for the over the time. With this let me complete the simulation. So, in the summary, we have started with the Kendall notation, and the MM1Q is discussed. Stationary distribution, waiting time distribution, response time distribution is discussed for the MM1Q, and also the time dependent solution, and I have given the simulation of MM1Q also. These are all the reference books.